Welcome back to STEM for Other, everyone. Today we will be starting our AP Chemistry um, tutoring videos. I'm Alexander Liu, and you can call me Alex. For today's unit, we will be working on atomic structure and properties, which is the first unit. These will be the subtopics that we will be going over in this unit. In today's video, we will be going over Unit 1.1, moles and the molar mass. Now, let's start with something similar. When you go to the store and buy eggs, you don't buy them one by one. You buy them by the dozen. Why? Because it's much easier to say, I need 2 dozen eggs than I need 24 eggs. The dozen is simply a convenient counting unit. In chemistry, we have the same problem, but much bigger. Atoms and molecules are incredibly tiny. So tiny that even a grain of salt contains trillions and trillions of particles. We need a counting unit that makes sense for these enormous numbers. That's where the mole comes in. 1 mole equals exactly 6.022 times 10 to the power 23 particles, and this number is called Avogadro's number. Whether we're talking about atoms of gold, molecules of water, or ions of salt, 1 mole always means the same thing, 6.022 times 10% of 10 to the power 23 of them. Think of the mole as the chemist's super dozen. It helps us count things that are too small and too numerous to count individually. So why do we need moles? Let's talk about that number, 6.022 times 10 to the power 23. How big is that really? If you could count one number per second without stopping, it would take you about 20 billion years to count to Avogadro's number. That's longer than the age of the universe. This gives you an idea of just how incredibly small atoms and molecules are. Now, what exactly are we counting with this number? It depends on what we're working with. If you have an element like carbon or sodium, you're counting individual atoms. So 1 mole of carbon contains 6.022 times 10 to the power of 23 carbon atoms. If you have a covalent compound like water or carbon dioxide, you're counting molecules. 1 mole of water contains 6.022 times 10 to the power 23 molecules. If you have an ionic compound like table salt, you're counting formula units, the smallest repeating unit of the compound. 1 mole of salt contains 6.022 times 10 to the power 23 formula units of NaCl. The key point is this. Avogadro's number is universal. No matter what you're counting, 1 mole is always 6.022 times 10 to the power 23 of those particles. Now that we understand moles, let's connect them to something we can really measure in the lab. Mass. Molar mass is the mass of 1 mole of any substance measured in grams per mole. Here's where chemistry becomes beautifully simple. For any element, just look at the periodic table. See that number under each element symbol? That's the atomic mass. For molar mass, we use that exact same number, but change the unit from atomic mass units to grams per mole. Let's try this. Hydrogen shows 1.008 on the periodic table, so its molar mass is 1.008 grams per mole. Oxygen shows 16, so its molar mass is 16.00 grams per mole. Simple, right? But what about other compounds? Let's look at water, H2O. We need to add up all the masses of those atoms in the formula. We have 2 hydrogen atoms. 2 times 1.008 equals 2.016 grams per mole. We have 1 oxygen atom. 1 times 16 equals 16 grams per mole. Add them together, 2.016 plus 16 equals 18.016 grams per mole. This means that exactly 18.016 grams of water contains exactly 1 mole of water molecule. This is the bridge between what you can weigh on a balance and the number of particles we're actually working with. Now, here's where everything comes together. These 4 equations are your toolkit for solving virtually any chemistry problem. Let me walk you through each one with a simple approach. Mass to moles. When you weigh something and want to know how many moles you have, moles equals mass divided by molar mass. Think, how many mole-sized chunks fit into my total mass? Moles to mass. When you know how many moles you need and want to know what to weigh out, mass equals moles times molar mass. Think, if each mole weighs this much, what's my total mass? When you want to know the actual number of atoms or molecules, particles equals moles times 6.002022 times 10 to the power 23. Think, how many individual particles are in my moles? When you know the number of particles and need moles, moles equals particles divided by 6.022 times 10 to the power 23. Think, how many mole size groups can I make from these particles? Remember, moles are always in the center. You go from mass to moles, then from moles to particles, or vice versa. Moles are your connecting point for everything. Now, let's put this all together with a real problem. I'll walk you through my thought process step by step. So, how many molecules are in 36 grams of water? So first, we need to identify what we know and what we need. We had 36 grams of water, that's mass. We want to know what's the number of molecules, and that's our particles. And we already know water's molar mass is 18.016 grams per mole. That's from our previous calculation. And step 2, we need to plan our route. We need to go from mass to moles to particles. So we'll need 2 equations, mass to moles, then moles to particles. So we then convert mass to moles. So moles equals mass divided by molar mass. So moles equals 36 grams divided by 18.016 grams per mole, which equates to 2 moles of water. Now, does this make sense? We had 36 grams of water, and 1 mole weighs about 18 grams, so we should have about 2 moles. Perfect. Now, we need to convert moles to molecules. So molecules equals moles times 6.022 times 10 to the power 23. Therefore, molecules equals 2 moles times 6.022 times 10 to the power 23, which gives us 1.20 times 10 to the power 24 molecules. So think about this result. That's over a trillion molecules in just about 2 tablespoons of water. This shows you just how incredibly tiny molecules really are, and why we need the mole as our counting unit. Now it's your turn to apply what we learned. Here's a slightly more challenging problem that combines multiple steps. So how many moles are in 8.25 kilograms of AgNO3? Also, find the number of molecules. So this problem has a few twists that will test your understanding, so let's work through it carefully. But first, I want you to pause this video and try to solve it yourself. Okay, now step 1, we need to calculate the molar mass of AgNO3. We need to find the molar mass first, so let's break down silver nitrate. Silver, or Ag, is 107.87 grams per mole. Remember, I'm taking all of this molar mass from the AMU, which is under the element symbol. So nitrogen is 14.01 grams per mole, and oxygen is 3 times 16, which gives us 48 grams per mole. So the total mass is 107.87 plus 14.01 plus 48, and that gives us 169.88 grams per mole. Now step 2. Notice we're given 8.25 kilograms, but our molar mass is in grams per mole. We need to convert 8.25 kilograms multiplied by 1,000 grams over a kilogram to give us 8,250 grams. Now, always check your units. This is where many students make mistakes. Now for step 3, convert mass to moles. So moles equals mass divided by molar mass. Therefore, moles equals 8,250 grams divided by 169.88 grams per mole to give us 48.6 moles. Now we need to convert moles to molecules. So molecules equals moles times 6.022 times 10 to the power 23 molecules. So molecules equals 48.6 moles times 6.022 times 10 to the power 23, which gives us 2.93 times 10 to the power 25 molecules. Therefore, our final answers are moles of AgNO3 is 48.6 moles, and number of molecules is 2.93 times 10 to the power 25 molecules. So there are some key lessons from this specific problem. You should always calculate molar mass first for the compounds. Make sure to watch your units carefully to convert kilograms to grams when needed, and to always use the systematic approach, mass to moles and moles to particles. And make sure to not forget the significant figures in your final answer. For this specific one, the significant figures are 3